Welcome. This is session, the first session in week 7. And in week 7, we do have 3 sections, 3.2 and 3.3. I will talk about section 3.2, and this section covers the mean value theorem. That means this one is like another existence theorem. We remember the intermediate value theorem from chapter 1. We were proving that with the certain scenario, a certain numbers exist. Now we will do similar things. A little bit different scenario and some specific numbers exist. Okay, that's this. And section 3.3, which will be covered tomorrow. Section 3.3 actually talks about the minimum and maximum value. Talks about different things also, but I'm just referring to the minimum and maximum and minimum value of the function because I saw some questions on the discussion. That means from section 3.3 we will learn how to distinguish the difference looking at the critical points, how to distinguish the difference if they are maximum values or minimum values for the function. Okay? That means we will learn like how algebraically, how looking at the formulas, we can find out if this is, at this point, we have maximum or minimum value. And that means this will be much, much easier. And I will also do the practice problems for you, practice with Kasia. I did last week, but I only did the PDF form because I had some issue with the recording. But this week, even if my voice is not really clear, I will still try to make this short video. All of the essential problems for section 3.2 and essential problems from section 3.3. If you will watch it, if you will practice with me, you will be successful in this week's assignments. Okay, let's start. The mean value theorem. Before we will try to talk about this, let's look at a little bit different theorem. Okay, and the different one is the ROLLE'S theorem. It's the name of the mathematician name. That's the reason that we have the name of the theorem like that. And let's see what we need. We need a function that satisfies the following 3 hypotheses. Function must be continuous function on the closed interval from a to b. Then function must be differentiable on the open interval from a to b. This means that we're not including the endpoints. A and B is not the condition for the differentiable. And we remember, in order for the function to be differentiable, the graph must be nice and smooth, no sharp corners, no gaps, no jumps, just the smooth curve, like polynomials, for example. And then the third condition is the value at the endpoints, f of A, must be exactly the same like f of B. And then there is, yes, that's what I was saying, we don't even have to compute sometimes the number C. We don't have to. Using that tool, we will prove that there is a number C in the interval A from A to B such that derivative at C of the function f is 0. Okay, that means graphically, we know what this means. Okay. If derivative is 0, can you tell me what's the position of the tangent line for the curve if derivative is 0? At the point C, what will be the position of the tangent line at that point? Daniel, thank you. Horizontal, yeah, Joe said 0, but horizontal tangent. That's we can see. We saying that if we have, and I can show you a picture, yeah, let's see, I have 4 different ones. Let's maybe take this one, that's the typical A. Let's start with the second one, third and fourth one. I will switch off my video, okay. And then we can see, let's look at the second. We have value f of A, the same like f of B. They are at the same level, okay? And then I have to connect them in the nice, smooth way. The function must be differentiable. Of course, continuity is also a big part of this game. And then I will definitely find a point that I can draw a horizontal tangent. This means that derivative at this point, which is the slope of that line, of the tangent line, is 0. Okay? That means this is always the case. If function is continuous, differentiable, nice and smooth curve without any sharp corners, and if the value of A and at B, it's exactly the same. As we can see, I can even like connect them. They also create a horizontal line if I connect them. Or I can have just the line. That's the easiest thing, because the line, tangent line to the line is the same line, or that means every single point in the interval from A to B is giving me the derivative 0, because derivative is 0 for every single number. Yeah. That means if derivative is 0 for every single number in that interval, we can say, yeah, the function is constant function, horizontal line. Okay, that means that's the property. And we know mathematics is about like shapes, patterns, paths. We always looking for some connections, and we using this. If the function is satisfying all of this condition, we always have horizontal tangent. Okay. I can also say, looking at the second graph, I can say that average rate of change, because the average rate of change between A and B, we can see slope is 0, is exactly the same like the instantaneous rate of change. Yeah, that's also another like comments. Yeah, another point of view. Average rate of change and instantaneous rate of change. They are the same. They're exactly the same at the point C. The point C exists. Okay. And let's take one function and verify that this function satisfies the three hypotheses of the Rolle's theorem on the interval from 0 to 9. And function is defined as a square root of x minus 1/3 x. That's what we have. Definitely root function and the linear function. This is continuous function. This is continuous function. The subtraction or addition of both of the continuous will result in continuity. No problem. Function is definitely smooth. We don't have any corners because we will have just the values. No gaps, no discontinuity. That's when function is differentiable. We never include the endpoints because we do not define derivative at the endpoints. And that's we consider as a sharp corner. Okay, and now f of 0 is f of 9. Let's actually check. If I substitute 0, of course it's 0. But if I substitute 9, square root of 9 is 3, and 1/3 times 9 is also 3, 0. Okay, that means this is fine. That means what I can say? I can say that definitely between 0 and 9, we're going to have a number, okay, that derivative at this number is 0. Yeah, that's the thing. Oh, I do have derivative, but what I wanted to say this conclude that the derivative at the certain number, let me just put x for now. That x will be c. It's equals to 0. Okay, and what we can do, sometimes for some modeling, some programming, coding, it's just enough to know that information. Okay? Like I will know that between 0 and 9, I do have a number c. Okay, I can put c belongs to interval from 0 to 9. The derivative at c is 0, which means the slope of the tangent is 0. Depends what we're doing, depends what we need. This will be enough and will be quite sufficient information. Okay? But what we can do in this case, since the function is relatively easy, we can find the derivative, we can define properly the left-hand side, and we can solve for x. That x will be c. Let's actually check. Derivative of the square root of x is 1/2 square root of x. Derivative of 1/3 x is 1/3, negative of course. Okay, and this is 0. Let's get oh, I thought that I make a common denominator, but we can do this way. We can add 1/3 to both sides. We can cross multiply. 2 root x times 1 equals to 3. Okay, and dividing by 2, I have 3/2. Now I will square both sides. If I'm squaring both sides, I have x on the left and 9/4 on the right-hand side. And 9/4 is definitely a number between 0 and 9. Right? As we can see, that's my magic number, C. And derivative at C, derivative at 9/4 is definitely 0. We can even try, but of course we don't have to. We can put 9/4. Square root of 9/4, it's 3/2. 2 is cancelled out. 1/3 minus 1/3, it is 0. Yeah. So that's the tools. The tool at the moment, because we still approaching the mean value theorem. Okay, let's look at the second example, for which functions below is Rolle's theorem applicable on the interval from -8 to 8. Okay? That's, we know what we're looking for. We're looking for the function continuity. Function must be differentiable, and the value at the endpoints, in this case is -8 and 8, they have to be the same. Okay, that's, what do you think about x squared? About the first function, x squared. Does this function satisfy all of them? Yes, it's definitely nice and continuous function. Okay, that's the function. And what about the value for -8 and for 8? Is the value the same? It is the same. Can you tell me the value? That's, thank you very much, 64, of course. Okay, that's definitely, I will check, I will check this function. This function is, what I can do, I can maybe put continuous function. We know that it's on that interval. Differentiable, and the value at -8 is the same like the value at 8. Okay, that means I can check all of. Okay, that means that's the condition for the Rolle's theorem. Okay, what about x cubed? Do you think x cubed, it's nice and smooth curve, continuity, differentiability, we satisfying. But what about the value? What about the value for -8 and for the +8? Yeah, it's not the same. Thank you, Jeffrey. It's not the same, because if I will cube, that's actually a huge number. If I will cube -8 and if I will cube positive, that's cube +8, I'm not getting the same value. That means this function is not good. Yeah. Okay, what about the inverse function for x cubed? Cube root of x. Let me organize the page a little bit. X to the power of 1/3, or if we prefer cube root of x, is just the inverse function to x cubed, which looks like that. The only thing that I would like to draw, this is my first function. I still would like to sketch really quickly, because I hope we remember x cubed. Okay, we have to remember that at 0, that's not a problem. Function is x cubed. I'm still talking about x cubed. It's still differentiable and continuous function, but at 0, this function has a horizontal tangent. Right? It's a horizontal tangent. I mean, that's different. I'm just saying this like as additional comments, because we still have different values for -8 and 8. But what's happened, if this is horizontal tangent, now I have the inverse function for x cubed, right? Cube root of x, which means at this point, we do have a vertical vertical tangent. And this means that slope of the vertical line, what is actually the slope of the vertical line? The slope of the vertical line, vertical tangent is, we can say infinity. It's simply right. It's simply undefined. Okay? That means this function doesn't have derivative at 0, which means function is not differentiable. Yeah? But of course, even if we miss this, I still don't want you to miss this. You will figure out based on the values, because cube root of -8 and cube root of +8, it's different values. Yeah, that means I can say the same thing. The values at the endpoints are different. But also, please remember, I don't know, just in case if we need different function, but also please remember the function is not differentiable at one point from that interval. Okay, that's we have x cubed, we have cube root of x. Oh, I don't want to cross my cube. Okay. Now what we need, that means this function is also not good for the ROLLE'S theorem. Okay, what about the function x to the power of 2/3? That means similar to this one, but we're gonna square all of the values. That means this will be a little bit higher, and all of these negative values will become positive. Okay, that means function number 4, x to the power of 2/3, looks like that. Oh, it should be nice and symmetric because we're squaring the values. Oh, I don't know if it's symmetric, but okay. And we can see what we have, right, in that 0. Function is, we have the cusp, corner cusp, which means the same thing. Derivative at that corner is not defined. That means right away we see that we don't have, we're not satisfying the ROLLE'S theorem. And can you tell me the values for -8 and +8? I believe they have to be the same, but just a little bit of arithmetic. What are the values? 4? Oh, how did you get so fast? Cube root of 8 to 2 squared 4. Thank you. I was checking you. Yes, 4. Thank you. That means we do have the same value, but we're not satisfying derivatives. Okay. That means this function, let's come back to our list, is also not differentiable. Like probably you remember I gave you like 9 graphs we call like a parents graphs or fundamental graphs. Yeah, and they are really helpful it's really helpful if you know them right away and then apply some calculus concept. Okay, number 5. Square root of not square root, absolute value of x. Yes, thank you, Ryan. Function is continuous function, but it's not differentiable. I can maybe draw the graph here. Yx, we can see we do have a beautiful corner, right? That means this function, it's not derivative at 0 is undefined. Good. Okay, now I hope we know that graph, number 6. Let's see. Number 6 is square root of 64 minus x squared. Do you possibly know the shape of this? I know, looks terrible, right? Okay, but what we can do, let's try to rearrange a little bit the numbers. I will try to square both sides, this equation. Then I will have something like that. And I will add x squared to both sides. Do you recognize this? X squared plus y squared is 64. It's a circle, right? Right. But now we have to be really careful. Now what we have to imagine that I'm giving you this equation, okay? And I'm asking you to solve for y. In other words, we have to come back. That means solving for y, I will subtract x squared, and then I will take the square root. However, taking a square root, I do have positive and negative square root. We know, like, taking the square root of both sides. And since my original question only have positive square root, I will only take a positive, which means the upper. I will not take this part. Okay, and this is, of course, 8 and negative 8. That means this is positive square root, represents the positive semicircle above the x-axis. Okay, that means this is the graph. We have values at 8 and negative 8 are the same. They are 0. And what do you think? Is this function continuous and differentiable between negative 10 and 8? Yeah, nice and smooth curve. Yes, thank you, Joe. Yes, no corners, no. Of course, we're not looking exactly at 8 and negative 8 for the derivative. Yes, Nitya, thank you. That means this function definitely, I can say, definitely satisfies the Rolle's theorem. Really good, nice function. Yes, really nice. Okay, and then we have the last one, number 7. Number 7 is x squared minus 64 an absolute value. Let me just check mine. Okay. That means absolute value. How can we draw this function? First of all, we can try to get the graph from inside, like the graph of the function inside. And inside, I do have x squared, which looks like that. Okay, and minus 64, how this negative 64 is affecting x squared? Do you know what kind of transformation I have to do? If I'm subtracting 64 from the entire value, I have to down. Yes, thank you. That means I have to drop down. Oh, my parabola. I have to drop down 64 units my original parabola x squared. Okay, that means, but this is just the function from inside. Now, taking absolute value of the number, what's happened? The values that were positive will stay, because absolute value of positive number is the same number, right? That means, and this is, of course, negative and 8. We know that. Okay. That means absolute value of positive numbers are positive numbers. Absolute value of negative numbers will become positive. That means I will do the reflection about the x-axis. Okay, I don't need this. Okay, that means that thick graph, it's the graph of x, absolute value of the quantity x squared minus 64. Okay. And what do you think? Is function continuous and differentiable between negative 8 and 8? Yeah, Adam said it's not differentiable. But what's happened? If I will, can you see? It's almost the same situation like for the circle. It's not differentiable exactly at negative 8, but the condition, or negative 8, right? It's perfectly fine. If I will ask, let me expand this interval. If I will ask if this function satisfies the Rolle's theorem from negative 10 to positive 10, then we can point negative 8 and 8 as numbers that a function is not differentiable. But since we do have given interval like this one, we're looking for differentiability from negative 8 to positive 8, not including these points. It's the same thing, right? Because we do have sharp corners, and it's perfectly, I like that you notice that. Derivative is definitely not defined, but what I'm taking only that part of this function. Okay, only this part, which means for the derivatives, I'm not looking exactly at negative 8 and 8. That means function is definitely continuous function, definitely differentiable. We can see I'm not including negative 8 and positive 8. And values are the same, yeah, which they are 0. That means I think we are satisfying the condition of the Rolle's theorem. Okay, that means this was nice exercise just to show you how we can analyze all of these functions based on our property. Okay, but still good answer. Yeah, still good answer for -8 and +8. Okay, let's keep working. We will skip this. Okay, that means this is just like a quick note about the Rolle's theorem, like how we can apply, and especially for some moving objects. We can say that if that's what I just said, that if the object is in the same place at 2 different instant time at A and B, which means the values at f of A and f of B is the same, this theorem states that there is some instant of time. That means this is a number of, the time c, yeah, we can see again, exist. There is some instant of time c between A and B, that derivative, which means velocity, is 0. And a perfect example is to see when the ball is thrown directly upwards. Yeah, it's throwing upwards, and then it's that moment that is at rest, and then it's going down. Yeah, that means just a little bit different perspective. Okay, that means now we have another mathematician, French mathematician, Joseph Lagrange, and he defined this Rolle's theorem a little bit different. Okay? It's almost the same, but we have a little bit different conditions, and we will call mean value theorem. And let's see. The mean value theorem is telling me this, that if the function f, it's continuous on the closed interval from A to B, the same like above. Function is differentiable on the open interval from A to B. Okay, nice and smooth, no discontinuity. Then there is a number, okay, number c in that interval, of course, such that, and we will probably use that form. That's the same, but we will use this one. Such that f prime at c, derivative at c, or slope of the tangent at c, is equal to this, f of b minus f of a b minus a. Okay? And you probably recognize this is the slope of the secant line between a and b. The only condition that is missing, we don't really have to have exactly the same values for A and B. Okay, we don't have to. Let's look at the graphs, and they look like that, really nice. That means now it's kind of like shifted, right? Instead of having a function like on the same values, yeah, and horizontal tangent, we kind of drop it, which means the value at A, it's different than the value at B. Okay. But now what this theorem is telling me exactly the same thing. If function is continuous and differentiable, then connecting these 2 points, now it's not horizontal line. Connecting these 2 points, I can nicely compute the slope, f of b minus f of a b minus a. Yeah? That means this slope is exactly the same like the slope of the tangent at some point between A and B. We have to find a point, yeah, somewhere that if I will draw a tangent will be parallel. Okay? Or we may even have few points, depends on the function. This is my secant line connecting A and B. Okay? That means the slope of this is f of b minus f of a b minus a. And then I can definitely find a few points. In this case, it's 2 points, c sub 1, c sub 2. That tangent is parallel, which means it's the same, has the same slope. And let's look at my comments. The slope of the tangent line is the same as the slope of the secant line. Of course, this should be at that C point, at C. Okay? And slope of the tangent, slope of the secant. That's my formula. So, right? That means this is the mean value theorem. It's also a nice property. We can prove lots of different mathematical theorems later in calculus 2, 3, differential equations. Okay, we can prove it. Because one thing that is nice looking at this formula, it's nice connection between just the function and the derivative, right? As we can see, it's always when we have continuous and differentiable function, if I will pick 2 points, the slope between these 2 points is exactly the same like the slope of the tangent line at some point C between A and B. That means tangent line is parallel to the secant line. Or I can say instantaneous rate of change is exactly the same as the average rate of change. Right? No, that's actually, that means instantaneous velocity. Yeah? It's exactly the same like average velocity. Instantaneous velocity, of course, at some point. That means, for example, this. For instance, if the car traveled 180 kilometers in 2 hours, you can definitely tell me the average. Yes, the average speed is 180 divided by 2, it's 90 kilometers per hour. Yes? But that's average. But what's happened? The speedometer must have read 90 kilometers per hour at least once. That means when we're driving, because the average is not telling me that I was driving constantly 90. No, I could drive a little bit faster, a little bit slower, but definitely at some point I was driving 90. Yeah, that means at that instant, that instantaneous velocity was 90. Yeah. Yeah, and that's what I just said. We may have, looking at the mean value theorem, we have the information about the function, just the function, and its derivative. Okay, and let's see how we can use this. Let's look at this example. Use this graph, okay, to estimate the values of C that satisfies the conclusion of the mean value theorem from 0 to 8. So when you get ready, you will tell me, let me put the scale, and you will tell me the C points. 6, 7, 8. And I believe that's the Y axis. And this is, oh, I have to be, okay. What I can do, yes, okay, oh, okay, you're looking at the, let's see, probably, what I will do, first of all, because that's my point A, that's my point B. Oh, can I connect these two together? Oh, wow, I did. Okay. That we can see, this is the average rate of change. The slope is f of 8 minus f of 0, 8 minus 0. And now we're looking at the values somewhere that drawing a tangent, I will have the same slope, parallel lines. And Ryan said 3.5. Oh, but 3.5 will give me horizontal. Can you see? If I will draw at 3.5, these two lines are not parallel. Ah, okay, that's when you gave me the horizontal. You gave me the condition for the Rolle's theorem. Yeah, that's mean we can't really use them. But okay, Jeffrey is saying 3. Maybe. I think so. We can say, because I need the line somewhere. Yes, I think 3 will be good. Let me try. Oh, I'm even quite, yeah, I think 3 is the good point, because the value of the slope, it's exactly the same like this one. Yeah, good. It's parallel. Okay, and one more. I think one more. What do you think? Where will be the other point that I can draw other red dot? CS, Daniel and Joe, 6.5. Yeah, somewhere. I will try to draw. Oh, I will try to draw. Oh, no. Okay. Yeah, I can accept 6.5. That means derivative at 6.5 is the same like the average rate of change, like the slope of the secant line, okay? That means you definitely find, I hope you understand the mean value theorem. We found the point C, 3 and 6.5. Really good. Okay, let's keep moving. Okay, that means this one is the typical. Verify that following function satisfies the free hypothesis of mean value theorem. Actually, should be 2, because we only have continuity and differentiability from 0 to 2. Okay, that means it's polynomial function, x cubed minus x, no problem. We do have continuity, each number is in the domain, no discontinuity, and function is definitely smooth function. Okay, that's actually that's what we have to do. We can still try to find the number C. Okay, we can say that the derivative at some point C is exactly the same like the rate of change on the average rate of change, f of 2 minus f of 0, 2 minus 0. And I will put the derivative of this function, and we can use C. 3x squared, 3c squared minus 1. That's what I have. And then 6 over 2 is 3, plus 1 is 4. And we can solve for c squared. And then we can take the square root of both sides. 2 over square root of 3. But plus or minus. And we can see we can't really accept negative in this case. Probably when I will make my interval wider, then I will accept both of them negative, but I have only, my domain is only from 0 to 2. That means positive should be checked. Remember this, always check everything against the domain. Because now the little feedback from your last week quizzes, the critical numbers is the same situation when you know what to do for the critical numbers, but always check if they are in the domain of the function. If they are not in the domain of the function, we can't accept them. The same here. That's our limitation, that's our constraints. Okay, let's see. Oh, we do have this function, but don't worry, it's the cubic function, we don't have to. And probably, yes, if I will draw another tangent here, which was that negative values, we will have also parallel. What was the value? 2 over square root of 3. And I believe this will be somewhere, well, this will be negative 2. But we don't have to take this number because we're only looking between 0 and 2. Okay. Okay. Another typical question. Find the number C that satisfies the conclusion of the mean value theorem for the function 9x squared plus 5x plus 6 on the interval from negative 5 to 5. I think this is a nice function, parabola, and open up. I will not draw it at the moment, but when I will draw this parabola, I think I have the graph. Oh no, I don't have the graph. When I will draw the parabola, we can try to draw it maybe at the end. But let's see. We have no problem. Function is definitely differentiable and continuous function. Continuous and differentiable. On the interval from negative 5 to 5. Actually, it's everywhere. Continuous and differentiable. Okay, and the mean value theorem, let's see. Derivative at some point C, this will be my point C, is the same like f of b minus f of a, b minus a. Derivative is the same like f of 5 minus f of negative 5, 5 minus negative 5. Okay, derivative. Can you tell me what's the derivative? What shall I put on the left-hand side? That's my function. Yeah, 18x plus 5, right? 18x plus 5, yes, thank you. And now I will put 10. A little bit of arithmetic. You have to help me. What is the value of f of 5? 9 times 5 squared plus 5 times 5 plus 6. Who can compute this one for me? 9 times 25 plus 25 plus 6. 901. This is, actually we don't even need a calculator. We have 9 times 25 and another 25. 10 times 25. Easy. 25 and 0, right? And then plus 6. Okay, I think that's 256. Let me divide the page. Okay, now we need the value at negative 5. Who can give me the value? 206, I think so, because this will be also 25, but this will be subtraction. That means now we have 8 times 25, which is 200 and 206. Thank you, Joe. Okay, that's what we have. We have 18x plus 5. Let me write a line, everything. And what's the number on the right-hand side? 50 over 10, 5. Thank you. Thank you, Raya. And then subtracting 5 from both sides. We're getting 0. No good. I can tell you always the simplest things are the most complicated. Yeah? That's actually what's always happened in all of the, I don't know, progress in our life. Progress, I mean some development. The simplest things are the most valuable, but it's not easy to figure out what is the simplest things. We always, making some mistakes. Okay, that means 0 divided by 18, of course, is 0. Okay, that means at 0, I don't know exactly how function looks like, but between negative 5 and 5, we do have values. How can I draw it? I'm just trying to use, I know that 6 at 5, no, I need negative. Okay, let me do this. At negative 5, we had this. I don't know if my graph, of course, the scale is huge. Okay, I will draw something like that. Oh no, that must be higher. Okay, this is 206. This is 256. Of course, my scale is terrible, but I don't have room to draw 256 units. And connecting this, right, we're getting the slope 5. We know where it is. And am I wrong? Because at 0, something is wrong, because at 0, when I draw a tangent, it's totally different. What I did, 6, okay, that means I really have to move everything. Right, that's not a good, let's see. I'm just trying to show you. I didn't plot the graph before. Okay, this one is, okay, I think I know. The graph will be like that. Okay, this is the value at 5. Now I think makes sense. This is the value for -5. Okay, and that's definitely 6 because I know that the y-intercept is 6. And still a little bit weird, but the slope at x0, which actually it's this, that's my tangent, must be the same like this one. Let me move this. Oh, terrible graph. Parabola. Okay, I will draw it like that. That's better. Okay, that's the slope 5. And this must be the slope 5. Yeah, but that's tangent. I hope I didn't mess up everything. And that red dot will be 256. I have to respect the scale a little bit. Okay, 256. Okay, makes sense. Still, they are not really parallel, but that's the point. If I will connect these 2 points and the tangent, we do have the same slope, 5. And it's at 0. Okay, let's keep moving. Okay, another typical question. Probably when I'm saying typical, you may expect questions like that. Okay, suppose that f at 0 is -3 and f prime at x is less than or equal to 5 for all of the values of x. Good information. How large can f of 2 possibly be? Okay. Yeah, probably weird question when we will not know what to use, but we're talking about the mean value theorem. Probably we have to use it. And I'm assuming since the derivative exists, because we can see derivative is less than 5, that means derivative exists for all of the values of x. Then function is continuous and differentiable. And what we're talking about? We're talking about the values at 0 and at 2. That means I'm assuming right away that we on the interval from 0 to 2. Okay. Oh. Okay. And we may actually, before I show you the normal arithmetic way, let's try to draw this situation and you will probably give me the answer. Maybe you even know the answer. Let's see. Value at 0, it's -3. Value at 2, because we're talking about the interval from 0 to 2. Again, I'm trying to. Okay, we don't know the value at 2. Could be one of these dots. Okay. But what I know that derivative for all of the values, it's 5. Or I mean, 5 is the maximum, or could be less than 5. Derivative means slope of the tangent. Okay, tangent line. That means I can say 5. Okay, that means I need slope 5 between the value at 0 and the value at 2. Let's say this. I don't know this value, but I know that the slope of this line is 5. Okay? Could be lower. Okay, could be lower. That means this dot is the maximum value of f of 2. Okay? And if the slope is 5, do you think you can tell me, just using the slope value, can you tell me what is the value of f of 2? Because rise over run, okay? Rise over run must be 5. Okay? A rise is defined as a f of 2 minus -3, because that's the value, and 2 minus 0. 7, I think it's 7, because this number, rise over 2, must be 5. Okay? And what number, because I know that this is 2, What number divided by 2 is 5? It's 10, right? But I've already have 3 units. That means in order to get 10, of course, that was the correct answer, Joe and Daniel, must be 7. Because 10 divided by 2 is giving me the slope 5. Okay, that's another way we can see how simple the property is. And I do have my definition, which is exactly the same thing. That's what we just did, rise over run of the average rate of change, okay? And then the derivative, okay? That means derivative, the maximum value of the derivative is 5. That means we're looking for the value of 2 with the slope 5. That's the scenario that I just drew it. Multiplying by 2, subtracting. That means the maximum value for 2 is 7. Could be lower, of course, because the derivative could be less than 5, but 7 is the maximum, okay? The largest possible value. Okay? Really nice question. I like this type of questions. Okay, do we have another one like that? Okay, something similar. If f of 1 is 15 and derivative now it's greater than or equal to 6 for all of the numbers between 1 and 7. Yeah? How small can f of 7 be? We can see the same thing. Now it's a little bit easier because they giving us an interval from 1 to 7. But even based on this and this, I can figure out that my interval is from 1 to 7. Oh? Because I want you to give me the answer. I mean, I can just show you this, that we're using like the mean value theorem. Function is differentiable continuous because derivative exists. This is my conclusion based on that. Then we can apply. Let's draw it. What values we have now? We have a little bit bigger values. At 1 is 15. And at 7, I don't know. Okay, I don't know where's the value, but I know that the slope 6, okay, this could be my value, f at 7, okay. But this is the minimum slope. The value of 7 could be higher, right? Higher, but the same idea. Do you think you can give me the value at 7? If we know that rise, 51, possibly, let's see, f of 7 minus 15, 7 minus 1. And the slope is 6. Slope is 6. That means what number divided by 6 will give me 6 actually? Easy, right? Because I need rise over a run. Run is 6. And I have to get 6 the slope. Let me use different color for the slope. Okay, that's because it's just coincident that it's 6. And it is 51. 51, if this is 51, I can put 51 based on Joe's answer. What color? I will use this one. Okay, what's the difference between 51 and 15? It is 36, right? That means my rise is 36. 36 over 6 is 6. That means this must be 51. Or I can say rise must be 36 because 36 over 6 is giving me the slope 6. That means 15 plus 36. It's 51. Really good. Yeah. Yeah, that means that. And could be higher. Of course, that's the smallest value. And I'm using the same thing. Average rate of change and slope. They have to be the same. I mean slope of the tangent. And we're just adding 15 to 36 because we need that 36. Okay, the largest possible. Oh, no, that's the smallest, right? I think I copy. That's the smallest possible value. Okay, And I think I have one more question and we will be done. That means what I will do, I will still practice a little bit and you can watch the video practice with Kasia, but I can tell you this session includes the most important question for this week from section 3.2, of course. Okay. Let me just, okay, let's solve this one. Suppose that derivative f prime of x is between 3 and 5. Okay, that's mean now we have like a limitation. We have the interval for the derivative for all of the values of x. Okay. Show that f of 8 minus f of 2 is between 18 and 30. That means this one is typically, we can definitely use the mean value theorem. Function is differentiable and continuous based on this statement. Derivative exists. And then I know that everything is happening between 8 and 2. Okay? And mean value theorem is telling me that f prime at c equals to this, the average. And I can say, actually, I wanted to do different because I wanted to show you what we can do. Because this, this is my derivative, right? F of 8 minus f of 2, 8 minus 2. And I know that this derivative, it's between 3 and 5. We can start from this or we can start from this, but we know that this is the derivative. And now it's just a few arithmetic steps to show that we have to isolate the numerator, f of 8 minus f of 2. And we can nicely see this is 6, 8 minus 2 is 6. If I multiply each side by 6, I do have 18, or I can even show multiplication by 6. This will be gone. And 5 times 6, of course, is 18 and 30. That means this one is like a kind of like a proof question. We have to show, we have to prove it. And based on the mean value theorem, we did. But I did start with my mean value theorem statement. Okay? Yeah, I think it's maybe less tangible question, but it's also based on the mean value theorem. Okay, and let me just check one more thing. I did. You can check. I did a little bit different because I kind of ended. I did this one. What I did, I start with the derivative being between 3 and 5. This one, I did show that actually derivative is between 3 and 5, which I believe this way, I was typing this way solution, but I believe this one is more appropriate, more relevant, because I did show that f of 8 minus f of 2 is between 18 and 30, just with the 3 steps. This one is I'm showing that f prime at c is between 3 and 5, which was actually given, but also the same idea. Okay. Okay, I do have. Okay, this is my last question. Let's solve it. Okay, and then we will be done. I know that I said example 8, but I do have one more. I promise this is the last one. Does there exist a function f such that f at 0 it's -1, f at 2 is 4, and for all of the x, derivative is less than or equal to 2? What do you think? We can try to draw this. Do I have, let me just draw it. I'm just trying to, okay, you can tell me. F at 0 is -1. F at 2 is 4. Okay, And then if I will connect these 2 points, I can get slope. Do you think you can give me the slope of this blue line? Rise is 5. And run, what is the run value? I think I'm correct with, yes, it's 5, thank you. 5/2, that's the slope, good. 5/2, which is 2.5. But let's see this. And they telling us with this condition, with these points, they telling us that the derivative for all of the values between 0 and 2, because I'm again assuming that my interval is between 0 and 2, all of the values of the derivative, which means the slope of the tangent, is 2 or less. That means, do you think this is correct? Does there exist? It's not, of course, because we got actually the slope just from this. We got bigger slope. That means this one, that is impossible since the derivative is less than 1. Derivative cannot be 5/2, so no such a function can exist, right? We don't have the function like that. The derivative for all of the x is less than 2. It's actually, we may have a derivative, we may have a less than 2, but not for all of the x's, because one of the slope we got 5/2. We can even get bigger. Yeah, that means this is definitely not the case, because if I will connect these 2 points, actually I don't know. This is just let's see, something like that. Oh, hang on, we need less than 2. Oh, doesn't matter. I can maybe something like that. I can have a slope smaller than 2, but at least I will have one slope like the blue one, right? Because I definitely have to find a point. That's what I'm saying. I will have at least one point C, that will have exactly the same slope like blue, which means will be not less than 2. The slope will be greater than 2. That means, this type of function doesn't exist. Okay, that's we do have 9 examples. Make sure that you understand all of them. Check, practice with Kasia also, and I'm sure you will be good for this week assignments. Thank you. Thank you for joining me, and thank you for the nice participation. I really like it, and I really appreciate that. You will see. Thank you.